So just in case people watch these videos who don't attend, I want to make sure you know you have a quiz on Friday the 18th. It'll be open the whole day Friday, so you have all 24 hours to take it. So if you have to work during the day, you can take the quiz at night. If you have to work at night, you can take the quiz during the day. Also, you have an exam coming up on September, let's see, 21st, Monday, open for 24 hours. You'll be able to take it anywhere during that 24 hours. And so if you work during the day, you could take it at night and so forth and so on. You want to set aside 2 hours for the exam. You want to set aside a half hour for the quiz. This week I'll be posting a couple more labs. Those labs are going to help you with the quiz and with the exam, so you don't want to dilly-dally on them. You want to actually try them. One of them is determining the formula of a compound from mass data, or called combining masses. Read about it in your book. And the other one is the formula of a hydrate, which you'll also find in your book. So the hydrate one is one where you're actually going to do something with the kit that I gave you. You're going to have to use the kit and an oven and your balance. And the big safety issue there is that you're going to be working with hot things. So to prevent any injuries, don't weigh hot things. Let them cool down. Oh, there's only the two of you. We lost one. Okay, so that being said, does anyone have any specific questions they want to ask about homework or anything like that?
Yeah. Oh.
All right, go ahead, Harry.
I have a question. Just with it's on the formula lab again, formula compound lab assignment. I just have a question with 4.
What does 4 ask us?
The nitrate ion is NO3 minus, and then it's how many electrons does it have total amount. Nitrate ion, if the nitrate ion was made of nitride ion and 3 oxide ions, what would be its formula? And based on your previous answer, how do we know that?
You can stop. You can stop. Right. So let's take a look here. So this is one of the polyatomic ions you're supposed to memorize. There are 7 of them you're supposed to memorize. This is the nitrate ion. So what are you supposed to memorize about this? Well, you're supposed to memorize that it has 1 nitrogen, 3 oxygens, and a -1 charge. Not someone. All right, Elizabeth, are you back? Well, we're going to go ahead and move on here. So that's what you're supposed to memorize about the nitrate ion. But if you look at the anions that you learned in the book, you learn that there's a C4 minus, an N3 minus, an O2 minus, an F -1. You might be wondering, why do I put a circle around this and why do I put the negative afterwards? Can I write -2? And the answer is I can if I want, but I put the circle around it so you know it's a charge. I don't put circles around things that are squared or to the 3rd power. As a redundancy, I put the charge after the number instead of before, because when you write something to the 2nd power or to the -2nd power, you always put the sign beforehand. So this is just something I do. So these are just some of the some of the monatomic anions that you're supposed to memorize, okay? And it's pretty easy to memorize their charge simply because of where they are on the periodic table. If you look at these in the periodic table, neon is 0, fluorine is -1, oxygen's -2, nitrogen's -3, carbon is -4. It's a number line. 0, -1, -2, -3, -4. And all of those in that particular column have the same charge as long as they're a non-metal. Okay? So carbon is the last non-metal. Here is silicon, so we don't really expect silicon to have a charge. Okay, so the nitrate ion is a polyatomic ion. So my question is suppose the nitrate ion was made out of a nitride ion and 3 oxide ions. So let's say that this was the nitrate ion. So this is a suppose. This is like suppose Tony's president. It's not true, okay? So suppose this is the case. What would the formula of the nitrate ion be? Well, it'd be NO3, 1 nitrogen and 3 oxygens. Is everyone with me here? Go ahead and say yes or give me a thumbs up or something. Are you with me here? Now, here's the tough part. What would the charge on this be if this was the case? Well, one of the things about charges is that they're additive. So, -3, -2, -2, and -2 adds up to -9. So this would be the nitrate ion if it was made out of 4 individual anions. This is in fact the nitrate ion. So if this were the case, if it were made out of 4 ions, and this is the real case, is it made out of 4 ions? What do you think, Harry?
No, I wouldn't think it would be.
It's not. It can't be because the charges don't match. So in fact, here's the nitrate ion. So this is the nitrate ion. And you guys see the lines between the atoms? Those are called covalent bonds. You find those in molecules, but you also find them in polyatomic ions. So the reason this thing has a -1 charge is because it has, let me think. Well, I can tell you. How many protons does it have? Well, it's got 3 oxygens times 8 protons per oxygen for 24 protons. It's got 1 nitrogen and 7 protons per nitrogen is 7. This thing has a 31 protons. So how do I know that oxygen has 8 protons? Well, because I can look at my periodic table, I see that the number at the top is 8. That's 8 protons. How do I know nitrogen has 7 protons? I look at the periodic table, I look at the top, I see a 7, it has 7 protons. So how do I know this has 31 protons? And the answer is I just add them all up. Now, if this guy has a -1 charge, does it have more electrons or protons? Who wants to answer that for me? More electrons or more protons with a -1 charge?
More electrons.
Absolutely. When you have a negative charge, you have more electrons. When you have a positive charge, you have more protons. So if we know it has, in fact, 31 protons and it has more electrons, how many more electrons? Turns out the size of the charge tells us. -1 means 1 more electron, so 32 electrons. If it had a -2 charge, it'd mean 2 more electrons, which would be 33, but it's a -1. All right, Harry, so does that help you with that number 4 on that one?
Yeah.
So the whole point there is when you look at these polyatomic ions, do not for a moment think about them being made out of monatomic ions and adding the numbers together to get the charge. It doesn't work. So if this doesn't work for the charge, so I'm gonna put a big X here, that's a no-no. How in the world do you get the charge? And the answer is you have to memorize it. So you want to memorize those 7 polyatomic ions that I suggested you memorize. It may be 8, now that I think about it. Good question, Harry. What's next? Remember, you can ask questions even about homework. I will show you how to do the homework if you're having trouble with it. How about the labs? You okay with the labs? I can help you with the labs. The whole idea here is you're supposed to work until you get stuck and then come up with a question, just like Harry did. What's going on with that one? And with that one, it wasn't so much work. It was like, Harry's question was more like, what the heck is Tony getting at? Right, Harry?
Right, yeah, no.
Yeah. And what Tony's getting at is these polyatomic ions are a weird bunch. Memorize them. Okay, you guys don't have a question. I'm going to put a very difficult problem on the board here from the first section, module 2, I should say. Module 1 wasn't really tough, but this is from module 2. And it's basically a calculation type problem. So you might want to find this in your book, and I can help you do that. If you have the 10th edition, you're going to look in chapter 2. And in chapter 2, it's going to be, let's see now. I want to say number 45. Or maybe it's not chapter 2. It's the review. I have to back it up. I think it's the review. And in the review section, there's a number 49. So if you're in the 10th edition, page 54, number 49. Does anyone have a different edition of the book? If you have a different edition of the book, let me know and we can find the page. Okay, so you want to have your book open to page 54, number 49, so that you can read this. This is a conversion factor problem, a unit analysis problem, a dimensional analysis problem. So the first thing I want to do is read it to you, and then I want to reread it and get the information from this problem. So fluoridation of city water supplies has been practiced in the USA for decades. Assume you live in a medium-sized city of 150,000 people. That's not a definition of a medium-sized city. They're just saying medium-sized people, city. So you live in a medium-sized city of 150,000 people. That 660 liters of water is used per day. This should say per person, not per day. What mass of sodium fluoride in kilograms must be added to the water supply each year, 365 days, to have a concentration of 1 part per million, that is 1 kilogram of fluoride per 1 million kilograms of water. And then they tell us that sodium fluoride is 45% fluoride and water has a density of 1 gram per centimeter cubed. So first of all, let's make things a little easier for us. Let's look at this name, sodium fluoride. Does everyone agree that this is an ionic compound? You should. The reason we know it's an ionic compound is because it has sodium in it, which is a metal, and it has fluorine in it, which is a nonmetal. So when you see a formula that has a metal and a nonmetal, your guess is it's ionic. Now, if this is ionic, the cation always comes first. So sodium's a cation, and we know it's a +1 because it's in group 1A. If it were in 2A, it'd be +2. Now, what about the fluoride? What's the charge on a fluoride? Well, if we go back to what I wrote earlier, you start at neon, that's 0, so fluorine is -1. Now, what is the formula of an ionic compound? Well, you put together the cation and the anion, and you must have enough of each so that the formula is neutral. In this case, if you have 1 sodium ion and 1 fluoride ion, that will be neutral. So how do you write the formula? NaF. Notice in the formula, you do not write the charges. Okay, so that's sodium fluoride. How about this guy, fluoride? What is fluoride? Well, that's fluoride. So the reason I want to go through that is that we can use the formula for sodium fluoride and we can use the formula for fluoride and not have to write out the words. So now we're going to go through a little bit of this. Assume you live in a medium-sized city of 150,000 people. So 150,000 people. You know, I don't know what that's really equal to. I suppose I could say one city equals 150,000 people, but I don't know that I need that. But I'm going to keep that in the back of my mind. 660 liters of water is used per person per day. If you want to write it out as a fraction, that's how you write it. Whenever you have the word per, oh, I see, this should have been person and this should have been day. This is fine. I just didn't finish up person. So when you see, darn it, when you see per, that means whatever follows goes on the bottom. Oh, we got another one. So whenever you see per, that means whatever follows goes on the bottom. So per person means put the person on the bottom. Per day means put the day on the bottom. People often ask, if you say per person per day, does that mean you put day underneath person? And the answer is no. The per refers to the water. And here, I'm even going to put water here. What mass of sodium fluoride in kilograms? So I'm going to put that over here. Kilograms of sodium fluoride. That's what we want. Must be added to the water supply each year. So here we got 1 year is equal to 365 days. They make a point of telling us that. To have a concentration of 1 part per million, that is 1 kilogram of fluoride is equal to 1 million. How do I want to write million? I'm going to put 1 times 10 to the 6 kilograms of water. And then they tell us fluoride is 45% fluoride and water has a density of blah. Okay, so sodium fluoride is 45% fluoride. What does that mean? It means that you have 45.0 grams of fluoride to 100 grams of sodium fluoride. That's what 45% means, 45.0. Now, do I have to use grams and grams? I do not. I'm going to cross that off and I'm going to put 45.0 kilograms of fluoride per 100 kilograms of sodium fluoride. So why did I choose kilograms instead of grams? And the answer is really simple. It seems like they're giving us kilograms to work with, not grams. So I want kilograms here. Now water has a density of 1 gram per centimeter cubed. So I'm going to put 1.00 grams of water is equal to 1 centimeter cubed of water. So these are all the things I have to start with. And I want to use them to start putting together my answer. So I'm going to put these up here. And I'm going to leave this off to the side here, because what I'm going to do here is I'm going to put kilograms of sodium fluoride. That's what we want. There it is. And so that's why I am putting this off to the right. So any questions about why I am putting this off to the right? Because that's where we want to end up. Now, if we look at all of the things that we can begin with, they are all equalities except for the 150,000 people. So normally, you want to start with a thing that is not an equality. And we want to figure out how to get from here, 150,000 people, to here, kilograms of sodium fluoride. And you can work a problem like this from the back or from the front. I'm going to start from the back. Do you see anything in here that has kilograms of sodium fluoride? This does, doesn't it? This has kilograms of sodium fluoride. So that means if I have kilograms of fluoride, I can get to kilograms of sodium fluoride. Okay. So, do I have anything with kilograms of fluoride in it that's not this particular one, and that's this one right here? So this means, because I have kilograms of fluoride here and kilograms of water, if I have kilograms of water, I should be able to get kilograms of fluoride. Now, do I have anything with kilograms of water in it? And I don't. I do have this, though, that has grams of water. So if I had grams of water, could I get to kilograms of water? And the answer is you bet your bippy. But that means here, to get to grams of water, I might need centimeters cubed of water. So you see how we're backing this up? Now, I'm a little bit stuck here because I have centimeters cubed of water, and I'm wondering where I get to that from. And I'm thinking it's got to be here somehow or other, but I'm a little confused here because I've got this. Now I'm just going to play with this. If I had 150,000 people and I multiplied by 660 liters of water per person per day, do people and person cancel? And my suggestion is they do. One is just the plural of the other. It'd be like saying do feet and feets cancel. That sounded kind of stupid. Nonetheless, I think that would cancel, right? And here, we get rid of the people, but we have the day. I think if we did the 365 days per year, days would cancel. And what we would end up with here is we end up keeping the year because we can't get rid of it. But we still have this liters of water. So can we get from liters of waters to centimeters cubed of water? And the answer is we should be able to, because here's the deal. We can go from milliliters of water to centimeters cubed. That's a lock because it's 1-to-1. Can we go from liters of water to milliliters of water? We absolutely should be able to. So here we've got kind of our pathway to get there. The only issue I see is that we're going to end up with this year on the bottom, and that means we'll end up with this year over here. And so our answer is going to be kilograms of sodium fluoride per year, right? Well, it turns out that when I wrote down my want, what I want, I didn't write it down very well. What's the question here? Assume blah, 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 blah. To have a concentration of, so here, they want to know what mass of sodium fluoride in kilograms must be added to the water supply each year. You can think of the word each as meaning per. So we actually want per year as part of our answer. So we want kilograms of sodium fluoride per year. Okay, so this is the pathway. Let's see if we can work it out. So 150,000 people times 660 liters of water per person per day. Now, how do I get rid of day? Someone turn on their mic and tell me what you want me to do here. How do I get rid of day? Don't be afraid. It's okay.
Shouldn't you put 365 days per year?
Right. Now for my want, I wanted year in the bottom, so I've got it. Now, let's talk about liters of water and milliliters of water. What is the conversion between 1 liter of water and milliliters of water? Does anyone happen to know it off the top of their head or want to venture a guess? This is one that you want to memorize because you run into liters all the time. And here's the answer. Does everyone see that? You should memorize that one. 1,000 milliliters is 1 liter, and that works for any liquid. So that is to say 1,000 milliliters of milk is 1 liter of milk. 1,000 milliliters of Pepsi is 1 liter of Pepsi. 1,000 milliliters of latte is 1 liter of latte. Okay, so here, if I want to get rid of liters of water, someone other than Jackie, what should I put on the bottom and what should I put on the top when we look at this conversion down here? Sooner you participate, the sooner you'll feel better about yourself and we move on. Come on, someone throw in.
You would put the liter on the bottom and the milliliter on the top.
Yes, 1 liter of water on the bottom so that these cancel, and 1,000 milliliters on top. So the way we do this is we look at the previous unit and we say, well, how do I get rid of that? Because I want to use the equality in that manner. So now we want to go from milliliters to centimeters, and you want to memorize this. One milliliter of any liquid is equal to 1 centimeter cubed of that same liquid. This works for water, milk, any other liquid you can think of, it works for. 1 milliliter of oil is 1 centimeter cubed of oil. Okay, so we've had Harry participate, Jackie participate. One of you other three, who wants to go next? Come on, just throw in, it won't hurt, I promise. Elizabeth,
I think
go
I
for
was
it.
muted in 2 different places because I joined on my phone. But
Okay.
we would want to put milliliters on the bottom. So we would do centimeters, 1 centimeter cubed per 1 milliliter so that we can cancel out the milliliters.
Right, and I do exactly what you did, Elizabeth. That is to say, rather than start with the top, I start with, well, I'm going to put this one here so it'll cancel. And therefore, the other one goes in the other spot. Does that make sense? So that's kind of what you started with. You said, I'm going to put the 1 milliliter on the bottom so it cancels. Perfect. Okay, now for the centimeter cubed to gram, we were given that 1 gram. Actually, we were given, 1.00 grams of water is 1 centimeter cubed of water. All right, there's 2 of you left, An and Jessica. Who's going to go next? How do we use this guy above?
I'll go next. So we'd use the 1 centimeter third water on the bottom and the 1.00 gram of water on the top.
Right. Okay, and you want to say 1 centimeter cubed, okay? If it's 2, you say squared. If it's 3, it's cubed. If it's 4, I say to the 4th power. Power means it's an exponent. Good job. All right, now we're going to go from grams of water to kilograms of water. And this is something you should also know. You need 1,000 grams of something to get 1 kilogram of something. So you need 1,000 grams of gold to get 1 kilogram of gold. And if you have that, you're kind of rich. Okay? So 1,000 grams of water is equal to 1 kilogram of water. So on, you're next. What goes on top and what goes on the bottom?
1 kilogram go on of water go on top and 1,000 gram go on the bottom.
Yes. Okay, so next we want to go from kilograms of water to kilograms of fluoride. And here we can see, I fold this over, from the reading of the problem, we have that 1 kilogram of fluoride is 1 times 10 to the 6 kilograms of water. So I'm going to take this next one then, and then August, you're going to be next. So here, I'm going to use this guy circled, and I'm going to put it up here on this fraction bar. Because I have kilograms of water on top, I'm going to put 1 times 10 to the 6 kilograms of water on the bottom because I want the kilograms of water to cancel. And if this goes on the bottom, the other side goes on top. Just like that. So we make our decision, again, based on what will cancel. So August, here's the deal. We have 45.0 kilograms of fluoride is equal to 100 kilograms of sodium fluoride. I'm going to circle that and square it. One of these two sides goes on the bottom, the other goes on the top. Which one goes where? So August, you'll have to unmute yourself.
August put in the chat that they just got their wisdom teeth out and can't talk, so they might be talking through the chat.
Oh, okay. Let me look at the chat then. So here's the question, August. Do you want me to put kilograms of fluoride on the bottom or kilograms of sodium fluoride on the bottom? So if you think it's fluoride, just put F. If you think it's sodium fluoride, put F minus. Let's see, where's the chat? How do you open that up? So do you want me to put, so here's how you have to answer, August. You answer, which of these two goes on the bottom? This is going to be the left, this is going to be the right. Do you want the left on the bottom or the right on the bottom? That's all you have to do. Type left or type right. And we're going to do it based on what will cancel. Okay, so you have right. So if we put this on the bottom, let's see what happens. 100 kilograms of sodium fluoride. So do you see that this and this don't match? So we don't want to do that. But nice try. Thank you for trying. So I'm going to erase that. And we're going to try the other side on the bottom. 45.0 kilograms of fluoride. And here, these match, so they will cancel. So we're going to put our 100 kilograms of sodium fluoride on top. So that's something you want to get used to, August, okay? Is you want to get used to deciding what to put where based on things canceling. So this is our solution. Now, we could estimate this answer. I'm not going to take the time to do it. You're not going to have a question on your test that says estimate the answer. So let me show you how I would put this into my calculator to get the answer as quick as possible. So what I do when I have a problem like this where it's all multiplication and division is I do all the stuff in the numerator first. So here's what that means. 150,000 times 660 times 365 times 1,000 times, I don't put times 1 in there because it's not going to do anything. And then we have times 1 times 1 times 1 times 100. I don't bother putting an equal sign in here. I just put divided by 1,000 and divided by 1 second EE 6 and divided by 45. Now you see this 1E6, this is the way that this is interpreted. That means 1 times 10 to the 6th power. So E means 10 to the. All right. So when I hit this, I think I get like 1.86 times 10 to the 12 is what we've got in another semester, something like that. Oh no, I'm wrong. I'm thinking about a different problem. So we get 80,300 kilograms of sodium fluoride. Now we have to decide how many significant figures does this have. Well, let me show you the ones that will limit what we get. It's this one here. This has 2 zig figs. This has 2 zig figs. This has 3 zig figs. And the reason it's 3 zig figs is because it's not actually 365, it's 365.25, right? Because of leap year. This is infinite. This is infinite. This is 3 zig figs actually, because water's density changes with temp. This is infinite. Now the 1 kilogram of fluoride to 1 times 10 to the 6 kilograms of fluoride, this has 1 zig fig, but we have to be realistic about this. What's the likelihood that your city is operating on a formula where they might use 1 kilogram or they might use 2 kilograms? I mean, think about it. If they're using 2 kilograms for every 1 million kilograms of water, that fluoridation is going to cost them twice as much per year. So can the city afford to spend twice the amount of money on their fluoride or fluoridation? Probably not. So this probably really is 1.0 kilograms. So I'm going to go with 2 zig figs. And here, this is 3 zig figs because 45.0 has 3. And the 100 is exact because when we talk about percentages, it's exact. So how do we write this with 2 significant figures? Because that's what we should have. And the answer is scientific notation. So I'm going to move the decimal over 1, 2, 3, 4 times. So I'm going to get 8.0300 times 10 to the 4 kilograms of sodium fluoride. And how do I write this with 2 significant figures? And the answer is you keep the 8, you keep the 0, you look at the 3 and you say, well, since that's below 5, we keep the 0 and we round down. And there's your answer. So this is kind of one of those ultimate conversion problems that, of course, I can't put on the test because it's way too long, but it's good practice. So I'm going to give you another conversion problem for you to do at home, where I'm going to give you all the conversions. You have to decide what goes on top and what goes on the bottom to get to the final answer. And you want to write it out as one long problem like this. Okay, so are you ready for that? You're going to convert 2.98 times 10 to the 8th meters per second to furlongs per fortnight. Because if you tell a colonial back in the 1700s that the speed of light is 2.98 times 10 to the 8 meters per second, they're going to look at you and go, well, I know what a second is, but what's a meter? What are you talking about? But if you tell them furlongs, they're going to go, oh, yeah, I know what a furlong is. Fortnight, they go, oh, yeah, I know what a fortnight is. And they're going to go, wow, that many furlongs? That's a lot. Okay, so here are the conversions you're going to need. You're going to need to know that there's 5,280 feet in 1 mile. All the conversions I'm about to give you are exact. You need to know that there's a 2.54 centimeters in 1 inch. You need to know that there's 12 inches in 1 foot. You need to know that there's exactly 8 furlongs in 1 mile. You need to know that there's 100 centimeters in 1 meter. You need to know that there's 60 seconds in 1 minute. And you need to know that there's 60 minutes in 1 hour, and that there's 24 hours in 1 day, and that 1 day is 1 week, and 2 weeks is 1 fortnight. This is the one where I think the answer is 1.86 times 10 to the 12, I think. But at any rate, these are all the conversions you need. what you want to do is kind of set this up and see if you can get yourself a little guidance for how to do it. So it might look like this: 2.898 times 10 to the 8th meters per second. You might have something like this: seconds goes to minutes, minutes go to hour, hour goes to day, and you could have something on top: meters goes to whatever. Get yourself a little pathway and then try and set it up. All righty? So what you should do with this right now is you should take a screenshot of it so that you got it forever and ever, instead of waiting for me to post this lecture, and see what you can do. Okay, that being said, I want to do some problems at the end of the next module, things that might show up on your test, or things that might show up on your test. But before I do any of those, does anyone have any questions? Any questions? Turn off your mic and just ask away.
This is Elizabeth. Sorry, I have a weird username. I just joined from a computer instead of my phone, so I could navigate this better.
Okay.
I haven't had a chance to look back in the discussion yet this morning, but I posted a question last night, but I thought it'd be worth asking here. In the lab, the lab naming compounds document
Yes.
for this week's lab, it mentions under polyatomic cations, it talks about the ammonium ion and it talks about the mercury 1 ion.
Yeah.
Is Hg2 with a +2 charge. And I was getting a little bit confused about that. I wanted to make sure that I was understanding correctly, because it seemed like normally the Roman numerals correspond to the charge of the ion for the variable charge
Right.
cation. But in this case, I did a little Googling, and as best I can tell, both the mercury 1 and the mercury 2 have a +2 charge, but one is comprised of one mercury atom and one is two of them.
Right.
Can you
Now
just
this
explain that a little bit more?
guy is called mercury 2. Okay. Now this type of name is used for monatomic ions. This is polyatomic ion. So polyatomic ions have their own naming system.
Okay.
And it's not really a system. It's just what we kind of like to do. For instance, like this guy here is called the nitrate ion. So this guy, we put the charge in Roman numerals. This guy, there's no charge written down. You just have to know it. You just have to know it.
Okay.
Now this
so,
one, what they decided to do was they decided, you know what? Kind of a good way to think about this is that just think about each mercury having a +1 charge. And even though it's polyatomic, if each one had a +1 charge, you'd call it mercury, whoops, not mercy. You call it the mercury 1 ion. I don't particularly like that name because it gives you the idea that it's a monatomic ion when it's not. So this is just named like a monatomic ion, but it's not.
okay, thanks. That was confusing me because it seemed like generally there was a rule, but
Yeah.
so
So you
this is an
understand why it's
exception.
called 1 though, right?
Yeah, because each component of the ion,
We pretend it has a
one.
+1 charge.
right, but if so then when, like on the practice sheets, one of the when we were going through and writing formulas from the
Yeah.
named,
So when you're drawing a formula for mercury, say mercury,
if it says mercury 1,
One,
it is
say
a +2
phosphate.
charge.
so let's say it's mercury 1 phosphate, right?
hmm
You'd have to know that this guy is Hg2 +2. This guy is PO4 3. You do the switch, so you get Hg, and this has to be a 2. Hg2 3, PO4 2, and that ends up being the actual formula because it can't be simplified.
Okay, great. Thank you for that. I think that's what I ended up with, but I got myself all confused with the naming convention on that one. So
Yeah.
just want to make sure I wasn't missing something
Mercury
fundamental.
one is weird.
Yeah, okay. Can I ask a logistical question on the timing of the quiz and exam real quick?
Yeah.
One of the previous Q&A sessions videos, you had mentioned that the quiz would be Wednesday and the exam Friday, but then I saw, I think, an announcement since then that said the quiz is Friday and the exam is Monday. So I just wanted to confirm.
Yep. They got moved back a little bit.
Okay,
So the quiz will be day after tomorrow. It'll be available at midnight 01, Thursday, if you want to call that. So right when the clock ticks 12 on Thursday evening, the exam's available. And it shuts down Friday at midnight. And I
Okay.
said the exam, and I should have said quiz.
right. So
So
quiz
it's
is on Friday.
for a 24-hour period. And the reason it's available for a 24-hour period is so that if you happen to work during the day, you can take the quiz whenever. And it works the same for the exam. The reason I have everyone take these things on the same day is so that there's less of a chance of communication between students about what's on the quiz or exam. Okay, any other questions? Okay, so I'm going to throw
Oh, it looks like August had typed a question in that we
Oh,
weren't seeing.
in the chat.
I'm trying to find the chat now.
I
think
have it
I-
here if
okay.
you want.
Yeah, I think I lost it when I switched devices.
In the
So-
isotopic analysis by mass spectrometry, does in atoms, molecules, and ions, lecture 7, why are there only 2 chlorine atoms in the peak at 101, 103, and 105? Does it have something to do with the electron gun in the mass spectrometer, knocking off electrons from some molecules of PCl3? And it's a good question. So during mass spectrometry, so I'm going to call this mass spectrometry. You have this molecule, PCl3, and you submit it to MS. And according to the book, we get some peaks at like 101, 103, 105. We also get some other peaks. And they have these things called the mother peaks. But the deal is that a phosphorus, there's only one type of phosphorus. For the chlorine, there's 2 types of chlorine. One of them is called chlorine 35, the other is called chlorine 37. This phosphorus is called phosphorus 31. These are mass numbers at the top. They are the number of protons and neutrons in the nucleus. So therefore, they are whole numbers. They can never, ever be fractions. So chlorine has 35 protons and 35, I'm going to say this again, 35 protons and neutrons total in the nucleus. Of those 35 things, 17 of them are protons. Therefore, the balance are neutrons. For this chlorine, 17 of them are protons. The balance are neutrons. For the phosphorus, I think it's 15. Yep, 15 are protons. The balance are neutrons. And this is one of the reasons why the standard symbol for these are written this way, is because if you want to figure out how many neutrons, you just do a little subtraction and you get the answer. And here, we always like to put the bigger number on top and the smaller number on the bottom when we subtract. That's just the way we were raised, and that's the way we do it. So this is neutrons, this is protons, and this is nucleons. Okay, so when you submit this guy to mass spectrometry, what happens is you get this guy. You knock an electron off. And then this goes to the detector and you detect. So what are the possibilities for this guy? Well, the possibilities for this guy could be this this, this, and this. So what I put together here are 3 chlorines that are from the 35 isotope and 1 phosphorus, because there's only 1 phosphorus. When we add these up together, we get 35 times 3 plus 31. So we get 136. What are the other possibilities? Well, you could get this. Now, what you're supposed to notice between the one above and the one below is that one of the isotopes is now at chlorine 37, which means you get a mass of 138. You could have 2 37s and 135, so you could have a 140, and they could all be 37s. So you're going to get 4 peaks, a 36, 136, 138, and 142. Now, the way these look is the 136 is going to be the biggest because chlorines are more, chlorine 35s are more abundant. So when you substitute a 37 for 35, this peak's going to get smaller. 2 37s for 2 35s gets even smaller and gets even smaller. So that's why the peaks get smaller as you get bigger. Now, one of the things that they don't tell you about mass spectrometry is sometimes these guys are unstable and they can fragment. So here are the possible fragments. You could get PCl2 or you could get Cl3. So what we're looking at here is taking off 1 atom out of all 4 of them. Now, if we get PCl2, you could have a phosphorus 31, a chlorine 35, and a chlorine 35. And here, if you do the work here, you get 101. That would be the mass of that fragment. Now, what if the fragment came from here and you knocked off a 35 instead of a 37? You could get this, and you could also get 2 37s. So if you're knocking off 1 chlorine, you don't know which isotope of chlorine you're knocking off, so you're bound to get 3 different fragments with masses 101, 102, and 104. Whereas here we got 4 different pieces. Here we only get 3 because of the combinations of chlorine. Here, what would we get? We could get a chlorine 35, a chlorine 35, and a chlorine 35, or a 35, 35, and 37, or a 35, 37, and 37, or a 37, 37, 37. Okay, this would weigh 105, if I did that right. This would weigh 107, this would weigh 109, and this would weigh 111. So when this fragments, do we think it fragments into PCl2 or Cl3? When we look at the spectrum, these don't exist. So that means this doesn't exist. So that means 1 chlorine is coming off. So that explains the 3 peaks at 101, 102, and 104. So what I need to know now is, does that explanation work for you, August? Excellent. So here the PCl2 can fragment, and we're going to get either PCl or Cl2. If we get Cl2, you're going to get a 70, 72, or 74, because they could both be 35s. And we don't see any of those peaks. So that means that when this fragments, we don't get Cl2. But if we get PCl, we should get a 31 and a 35, which is a 67. We should get a 31 and a 37, which is 69, and only 2 peaks. And when you look at the spectrum, do we get a 67 and a 69? And the answer is absolutely. So they ask you then, well, what about the structure of this thing? What does it probably look like? Well, if the chlorines are being picked off one at a time, chances are they're on the outside of the molecule being picked off one at a time. So this is what you would suggest as your structure of the molecule, because the piece that happens to be in every fragment is probably central to the molecule. And it looks like there's a phosphorus in every fragment. So you want to keep that guy in the middle. Okay? All right, good question, August. All right, what's next?
It looks like August did bring up another question. If we could go over problem 4 on the naming elements lab assignment.
Okay, what is problem 4? Oh, is that the nitrate one?
Let's see.
I think we may have done that one.
Yes.
So here's the quick deal on that. This is the nitrate. And the question is it made out of monatomic ions? If it were, it would be this. Now, if it were made out of this, the formula would be NO3, 1 nitrogen, 3 oxygens, but -9. Now, if you take a look at these two formulas, they don't match. One has a 9 charge, the other has a -1 charge. So is the nitrate made out of this? Nope, it's not. So the nitrate, and you don't need to know this right now, you will need to know it in a future chapter. The nitrate is actually made out of this. Oops, get rid of those. And this guy has a -1 charge. So the point of that exercise is to make you realize that you can't figure out the charge on a polyatomic ion by adding up monatomic ions. So how do you figure out the charge on this guy? And the answer is you don't. You memorize it. Just memorize it. All right, so that's the shortened version. If you go back and play this thing when I post it later, you'll be able to see a longer explanation, which is basically this. Okay, what's next?
Oh, I have a question about the quiz.
Yeah.
Like, in the quiz, do you give us like the convert like 1 inch equal 2 points? Oh, you had to remember it.
I don't give you, this is what I give you on the quiz.
Okay. Oh,
I give you a periodic table.
all right.
The
I thought
names
you
are
give me
not
the
there.
convert thing too.
The names aren't there. The symbols are. The numbers on top are there, and the numbers on the bottom are there. So you'll get something that looks kind of like this: H1 1.008, helium 2 4.01, lithium 3 6.9 something. You know, you'll get that, and that's it.
Okay.
So you're supposed to know those conversions. So what
Okay.
conversions, here's a good question, is what conversion should you know? And the answer is all of them. But let's look at metric conversions. What metric conversion should you know? All of them. So you should know that 1 kilogram is 1,000 grams. 1 milliliter or 1 liter is 1,000 milliliters. You should know that 1 kilosecond is 1,000 seconds. You should know that 1 mega dawn is 1,000,000 dawns. You should know all the metric ones. Now, there are some metric ones that pop up more commonly, so I'll give you the more common metric ones. So there's 10 millimeters is 1 centimeter. That's a common one. 100 centimeters is 1 meter. 1,000 grams is 1 kilogram. 1,000 milliliters is 1 liter. These are your most common metric conversions that you'll be using. Okay? But what if you wanted to know about a nanometer? What's a nanometer equal to? Well, you got to be able to figure that out. And here's how you do it. So this is the general way of figuring out a nanometer and a meter. So just the base unit. Here's the way to do it. So do you see what I've written there? 1 nanometer is 1 nanometer. If anyone argues with you about that, you should walk away because they're crazy. Now, how do I get the conversion? I take one of the prefixes and I put the number there instead. Nano means 10 to the minus 9. Now, let's say I don't like negative exponents. Then I change this to this. So how did I get from here to here? And the answer is I took the 10 to the minus 9 and I multiplied each side by 10 to the plus 9. And 10 to the plus 9 times 10 to the minus 9 is 10 to the 0, which is 1. 1 times 1 is 1. So I like to say that you can just take the exponent and put it on the other side and change the sign. So this literally says 1, what is that? Billion nanometers is 1 meter. So you need to be able to get those conversions and you need to be good at it. So real quick practice. I want you to get this conversion. 1 micrometer is 1 micrometer. What's the conversion? And I'm going to give you micro is 10 to the minus 6. So I want you to write out this conversion 2 ways, this way and this way. And just so that you can see it again, nice and clean. Micro is 10 to the minus 6. I want 1 micrometer is equal to something. And I also want micrometers is equal to 1 meter. I want both of those. All right, this would be the time where I normally give you more time to work it out, but I'm going to show you it step by step. Step 1, 1 micrometer is equal to 1 micrometer. Don't skip this step because this is the only step that you're absolutely certain of. Second step, keep the first micro and get rid of the second. And when I say get rid of it, substitute. So there's one of your conversions. Step 3 is take this negative and put it on the other side. And you're done. It's as easy as 1, 2, 3. Any questions about that? So those are all the metric conversions you just should be able to get. Any metric conversion. So, if I asked you for 1 decimeter, you should be able to get me a couple of conversions out of that. So that means you should memorize the prefixes. Other common conversions you should know, and I expect you to know. I expect you to know that 1 centimeter cubed is 1 milliliter. I expect you to know that 2.54 centimeters is 1 inch. This is exact. It's defined. So that means there's infinite zig figs in 2.54 and infinite zig figs in the 1. This is also exact. You should know those two. Other ones that I think you should know. 12 inches is 1 foot. 1 foot or 3 feet is equal to 1 yard. 60 seconds is equal to 1 minute. 60 minutes is 1 hour. 24 hours is 1 day. 1 day or 7 days is 1 week. Okay, so fairly common things in the United States. I don't expect you to know the mile and the feet because most people don't know that. If you do, that's great. If you don't, that's okay. So those are the kinds of things that you should memorize. And again, these are the ones that are most commonly used for metric. And so maybe you want to memorize those. All right. Let's see. We're at 8 after right now, so we've been going at it for an hour. Give me a thumbs up if you want to stick around for a little bit more.
I gotta go. Thank you.
That's all right. Thanks for stopping by. Well, no thumbs
Bye-bye.
up, so turn your mics on and say goodbye to everybody.
Bye,
Bye.
everyone.
Bye, everyone.
Hi, everyone. Thanks for all the great questions.
All right. Come back with more questions on Friday.